So I'm going to try to explain a bunch of things that I was confused by. I still kind of am, but I think it's a lot more clear now in my mind how it works. But obviously, take everything with a grain of salt and keep in mind that I'm using ChatGPT as well. I use ChatGPT a lot to help me understand these things and also to build examples. And I watch a bunch of videos and read articles and stuff like that. So I'm just gonna explain what I'm thinking right now about the most confusing part so far about learning Haskell coming from C++. Then after I do that, I'm gonna try to do these exercises here that I found. I don't remember exactly where I found this, in one of the videos that I was seeing or articles. And obviously I'm not really sure if I'm gonna be able to do it because I didn't try yet. I just forked the repository, I didn't clone, I didn't do anything. So if I can't do them, then I'm probably just gonna spend some time reading this book here, which I think is Haskell Programming from First Principles. I'm basically just studying Haskell, probably gonna look into the projects as well. So I'm gonna wait to see if it's streaming. Okay. So basically I did this scalar draw thing here. So the most confusing parts so far about learning Haskell coming from C++ is the concept of type classes. And I think that's also because I don't have a lot of experience with interfaces. But I'm gonna try to explain here how I'm thinking about this right now. So there's different ways of handling the relationship between different classes and different types in general. So one of them is the simplest one is the monomorphism, which means that type can only be one thing. So for example, this is like a normal function on C. Not really I think C as well. C does have type, but mainly C++ I want to talk about. So it's like when you have a function that has a parameter that the type is int, for example, you can only pass int to that function. So just one type. Then you have parametric polymorphism, which is more the concept of template, which would be like you have a generic function, is the example that I did here, that accepts a template. I forgot the template in the top here. But it would be a function that accepts a generic type. So it can be any type, as long as the type works on the whatever you're gonna do inside of the function. This part I'm gonna explain more once I explain all of them. But there are some nuances there that's still kind of confusing, and that's what I'm trying to clarify. But mostly it's gonna be like the template can work either as a bool, an int, or a float. But the important thing to understand is that the compiler is gonna resolve for only one type. So the functionality, the behavior of whatever is gonna happen in the function is bound by one thing only, and you don't have a different behavior depending on the type. So although you can have a bunch of different types, you only have one behavior. Then you have subtyping polymorphism, and this is the relationship of classes, class inheritance on C++. So it's how the compiler thinks about resolving the differences in types when it comes to classes. So this would be, for example, you have a class foo that inherits from bar. The behavior relationship is going to be a bar inside of foo. So bar is a set that is contained within foo. So basically foo has the behavior of bar and has additional behavior. So the behavior expands outside based on the set. The way set thinking, I think, I don't know how to explain this, but the type relationship is going to be the exact opposite, and this part's a little bit confusing, but when it comes to the type resolution, it's going to go inside. So the way that the compiler is going to think is going to be whether or not the base type is the one that encapsulates all the other types, and every time you have an inheritance, you're going to create a smaller set within that set, when it comes to the types. And the way that the compiler is going to be able to know whether or not you can use that argument is by going inside of the main set, which is the base set. But the behavior is exactly the opposite. So this difference here in this relationship is what causes object slicing on C++. So on C++, if you have a function, for example, that the parameter is bar, which is the base class, and you pass a class of type foo, which is a class that inherits from bar, and you don't pass a pointer, you pass the copy of the class, you're gonna slice the behavior of foo, the extra behavior of foo, which is basically the type of the set that is outside of bar here. Because although the foo type is inside of the bar type, so it means it's a valid type to pass to the function, the foo has additional behavior from type. So that additional behavior gets cut out of the structure, and this can cause a lot of problems. So this is like some nuance that is kind of annoying. But this one I'm not 100% sure, because obviously there are going to be nuances. So I haven't looked into the compiler source code very in depth to know exactly how. I know that object slicing is a thing, but I think it depends on the context and the way that. So for example, if you're passing a pointer, the object slicing is not going to happen, because the way that is going to work is that the pointer is going to point to the same location in memory. So the compiler is going to be able to resolve. But these parts, I'm not 100% sure, because again, like, it's going to depend on context and nuance, so I can't be 100% confident. But I know I am 100% confident about the object slicing. And the object slicing happens exactly because of this relationship, that there is a different way that the type relationship is expressed from the way that the behavior relationship is expressed. And this is the main core of the fundamental principle that is kind of hard to understand, is that there is a disconnection between what is considered to be a type and what is considered to be a behavior that is connected to that type. Because these things, sometimes they overlap and sometimes they're separate from each other. Not completely separate, but more separate, let's say. Then the next paradigm is this ad hoc polymorphism. And this is the thing that Haskell implements, the C++. The closest thing on C++ that implements this is concepts, which I'm not very familiar with. There's some YouTube channel that I'm gonna show the link to the video later. I'm gonna search there. But yeah, there is a video where he talks about, but I don't have a lot of experience with concepts on C++. So I think this is completely new from Haskell to me, which is more the notion of interfaces. Also, these videos here from these guys are very good. The 7 is probably the best. So I think so far he explains the relationship of types the best that I found. One of the best that I found is the 7 here, so highly recommend. And I'm going to show the other video later. But basically the way that this works is very similar to the template, but the difference is like you are declaring a templated function, let's say, but it allows you to specify a unique behavior depending on the type of that. Depending on the type of the type, if that makes sense. So it's as if you could determine on C++, if you have a templated argument, different behavior depending on which kind of type you are passing to the function. So let's say, for example, here, you could, for example, if you're passing an integer, you could say that the function is going to work like this. But if you're passing a bool, you could say that the function would work like this. So it allows you to change the behavior depending on which type you're passing to the function. And that's the main difference between ad hoc polymorphism and parametric polymorphism. So I'm not 100% sure if this is the accurate representation, but that's how I drew. So like the behavior is the intersection between all the types that are instantiated based on the class type. So the class type would be this thing in the middle. And this is like the diagram from when it comes to the behavior. But the diagram when it comes to the types would be just every time that you add a type to this, add a behavior or an instance to this type, it would be as if you are putting them here. So it allows you, for example, every time you call a function with the printable type, it's going to look for whether or not the type you're currently using is part of the printable type. That makes sense. And then based on that, it's gonna determine how the behavior of the function is gonna be based on the type. But this is the part that is very confusing. I'm probably gonna study more today about this because I'm still trying to clarify more how it works. But when it comes to the behavior, it's like this. So this defines the type. And then for each type that is part of this class type, you're going to be able to implement a unique behavior for that type. And the code that I got from ChatGPT, but I think is correct, is this one. So printable is a class on Haskell. So like this A here would be like the T that I drew there for C++. Would be like the generic template. And then this would be the definition of a function. So it receives a T template as an argument and returns a string. And then here would be the instances, which would be like the putting the type inside of the printable type. So you're basically specifying through Haskell, like if you use printable on a function and you to declare the function and you pass an integer to the function, this is what you have to do to implement the functionality of that function. So it basically allows you to have different behavior depending on which type you have. And this is different. So like this here, the way that this works would be as if you have the combination of both of this. Actually, on C++, the default is the combination of this. So that is the difference. So like on C++, you have functional overloading. So you can implement a function based on the you can implement the same function a bunch of times with the different arguments, but then the issue is you don't have the generic template. So either you have to implement the function of a bunch of different types with a bunch of different times with different types, or you implement once with the generic template. So if you're using the generic template, you're forced to have only one implementation. And if you implement with a bunch of different types, then you can have different functionality, but you lose the ability to have the generic function. So it's very similar, but it's more like the ad hoc would be the combination of function overloading with parametric polymorphism. So it's kind of like a merge between the two. You are defining function templates while at the same time having the ability to define different behavior based on that template for each different type. So I think that this is the main point of confusion. So from first principles perspective, is the way that the compiler is gonna think about the relationship between types and how that relationship between types is gonna determine behavior. So like the way that I'm thinking about it is that the type is the structure of the thing, and the behavior is the path from which the structure transforms into other structures. And then here is another thing that is very confusing, which is algebraic data types. So on Haskell, if you want to create a new type, what you can do is use the data keyword, and then you put the name of the type you want, and then you make it equal to whatever the type is going to be. So this would be similar to creating a string, for example, or creating something like creating a class. It's similar, but it's not the same, because this is related to the type and not the behavior. But it would be as if you have like a standard string or some other class. But the difference between these two here is the sets here, basically. So this is a product type, which means that in category theory, it's like multiplying the different templates you have, which would be A, B, C in this case. Which means that it works like a tuple or a pair on C++. So you're getting the intersection of the different templates to get a unique set that contains that intersection. So you would be like as if you could have like a string as the first argument of the tuple and an integer on the other one. So you're creating a new type that is the intersection between the string and the other one. And the way that the compiler is going to resolve, I think, is going to be similar to the mechanism that subtyping has, where it's going to, inside of the bigger set you are creating that has the types, is going to find the behavior that is specific to the current type you're using. But I think that this is more for this other situation here. So this would be like the union or the sum type, which basically allows you to put the generic types inside of another one, which is basically the new type you're creating. So here actually it's better to put as type, which is basically what you're doing here. And then the way that it's going to work on this, the way that the compiler knows how to deal with this is that every time that you're using this new type here, it's going to search for whether or not so let's say you are calling a function, you declare a function that accepts this type as an argument. Then you call the function passing the argument a, for example. Then what the compiler is going to do is going to see if if the type is inside of the main one that you created. And if there is, then it's going to look for how to deal with that function from that type perspective. So like how to deal with the behavior of the type. Another part that is very confusing is the type constructor, but I haven't dived too deep into this. But basically you can have another keyword here, I think. Like we could have type here, and this is going to be like the first one is as if it is not a type, would be like saying string, and then but this part is still, I'm not 100% sure how it works. So I'm probably gonna just study now with ChatGPT, or yeah. I think I'm gonna do the exercises now. And these parts are the ones that I'm struggling the most, and there's a lot of other stuff to study as well. But I think it's just confusing because there isn't a specific syntax to determine the arguments of a function on Haskell. So specifically on the class declaration here, I'm getting confused, I think. So there is, for example, in the situation where you have functors and monads, you're gonna have this relationship here, which is kind of like you're using it's like you're passing two different generic templates to a function. But then you're using that to pass, so like it's like you're currying the functions here. So the first argument would be, the first function would receive these two arguments, and then you would return another function, and then this other function would return this other type here. But it's very confusing to understand this syntax here and what exactly does this mean, the implementation. So I'm gonna see if I can do this thing here. Maybe I should show, oh, I forgot. I'm gonna show I'm gonna search for, I think it's CPP meetings or something. It's like one of the best videos that I've seen, meeting CPP. Is this channel here? Yeah, is this video here? Was one of the best that I've seen. He basically shows the different languages, and then he shows the relationship. So concepts, type classes on Haskell, traits on Rust, and protocols on Swift. So this video is very good, and these videos are very good as well. So I asked a bunch of things to ChatGPT also. So I asked for the examples, and I was asking a bunch of the relationship between these things. But I think that the main difference between the way that Haskell is going to work and the way that C++ usually works is that there's a lot more generic template programming, and there's like a class changes the structure and the behavior and creates a new type and that type has the behavior and the structure attached to it. That's what the class is. But I think a class type is just this thing is very similar, because it does have the definition of functions as well. I think it just doesn't have the structure, so it doesn't have extra variables and stuff like that. So the main difference is on the resolution of types on runtime and both on compile time on other functions. There's a slight nuance that changes a lot the way that it works. So I'm going to see if I can do this thing here. I did these 2 steps here. It's three steps. So I'm gonna try this one out. I was trying to avoid doing another thing here, but I think I should have cloned before. I think I did this wrong. So I'm gonna keep this thing here. I'm gonna delete this. I think should clone first. Got the link and clone. Think now I enter the exercise directory original. So course remote. I don't know what it means by this. What is the exercise repository? I think he's just talking about the clones, like the main thing. Yeah. So basically the thing there. You can verify that everything is done correctly by using the output. Yeah, I think that it is correct. Amend your solutions in a separate branch, not main. Can run the following command to create a new branch. I finished implementing exercises. Create a pull request to your fork. Once there already contains PR templates. Blah, show up a PR. I don't think I'm gonna do this stuff here. I just wanna see the main thing that I wanna. I'm not even sure. I don't know if I'm gonna be able to solve the exercises, but the main purpose I think for like the main focus on doing this is to think about what parts are struggling the most to try to understand from fundamental principles perspectives what exactly do I have to clarify. That's the thing that I'm interested the most. Is updating. I already did this. Should already installed the toolchain, I think. Yeah, so now should probably open this on VS Code and try to run make build. So make build is gonna run this make file here. There's always the reason I'm not 100% sure if I'm gonna be able to do it because there's always a question mark whether or not everything's gonna build. Yeah. So if sometimes you counter errors, it's gonna be very hard to solve them. Well, I think I found this. Well, the thing is, I forgot. I found this from I think it's kind of like a course. There were 4 lectures, but I forgot what. Maybe you can find by with a simple search there. It was a playlist with 4 videos, but I forgot what keywords I used to search this. Let's see if I can find on the history. I think it's gonna be annoying to figure out the how to solve the problem there. So I might not be able to solve the problems. But I think I'm gonna look into the code anyway. To if I can't re takes too long to maybe should put like 1 hour as a timer to see if I can solve the build problem there. And then if I can't in 1 hour, I just read the code. I think I found, yeah, I found the channel. So it's basically this guy here. I think it's uh, this playlist here. So I'm pretty sure that it comes from this playlist because this one has 4 lectures. And I followed there in the beginning, so the repos. I think the link is on one of the descriptions of the videos. It's basically this repository here. Let's see if I can solve this. Maybe you can try to build with this instead. Hopefully it's gonna work. I think Cabal uses Stack uses this file here probably to build, and then Make uses the Make file. it makes more for Unix systems probably. But it's like I use make on other projects, so I know it works here. And the reason why is basically because I installed the I think it's VS toolchain, so Visual Studio toolchain, which basically they provide you with executables that are gonna compile the codes. So I do think you can use make on Windows, but I think it's more like it's easier to use if you're on some Unix system, I think. And it's basically gonna run the code here. So it's using Cabal to build. I think you can use Cabal, which is gonna use this. Use make, which is gonna use Cabal, or use this stack, which is gonna use this file here, I think. So the things that are more the most confusing thing so far is definitely the type stuff, but I think it's becoming more clear. So the class type is like a generic the easiest way to think about it coming from C++, I think, is as if you have a generic template that also allows you to have function overloading. So it's a combination of a generic template with function overloading. And I think that the way you use it is whenever you want to create a new type that is going to have some you want to create some functions that are going to be this is the relationship that I'm not 100% sure yet how we like because the challenge in learning this is understanding in which context is going to work. So like obviously I understand the code there when you're reading, but I don't have a very clear picture on when should you use each thing and how it works in practice. Yeah, but basically you're gonna define the function on when you define the class, you declare or define the function inside of the class based on the type that the class is gonna have. So the class type it is kind of like a type of types. So the thing that makes it more confusing is that you also have kinds, which is a type of types as well. But I do think that's the class. It is kind of like a types of types as well. So you're defining a function that's going to be a generic function based on the template on the class there. And then for each instance of that type, you have a different behavior for that function based on whatever type you have there. And then you have something called deriving, which is going to allow you to implement for standard classes that they have the different instances, different functions that the classes use. So I have eq or eq, which is basically for equality, to testing equality. We have show, which is for printing stuff. We have ord for ordering stuff. So these are like class types that are built in Haskell that implement these functionalities for standard types, I think, for built-in types that they have. And then some types it doesn't require to redefine the functions because Haskell is going to be able to, like the functionality is going to work for your types as well. But in some situations you need to define your own functions as well. So you can't really derive directly because you're going to have to implement a new functionality for the type. Also, I should share the resources that so I have notes here. I have some pictures as well that I took. It's kind of slow because I think it's taking a lot of the CPU to build this stuff. This is basically the notes I have so far. So here is more for stuff that I wanna learn. I think that the functor, so the functor is kind of confusing because I've seen from some videos, from category theory videos of the guys explaining, but from the programming perspective, it's more like a structure. So functor would be a structure, or the way to preserve a structure between different types. And monad would be transition from one type to another while maintaining the structure. So the easiest way to think about it is a list, a flat list, or a flat map. So you take a list from one type and you transform the list to another type while still maintaining the structure, which is a list. But the syntax there is kind of confusing. There's also this applicative, which I don't understand very well. These things I'm gonna have to study more, I think. But it goes back to the first problem, which is they don't allow you to, like, just studying the topics don't allow you to understand, to have a good idea of how you're supposed to use these things on an actual program. That's the part that I'm struggling the most. Yeah, but this is basically gonna be, I think, the definition, or this one actually. So this one seems to be the definition of a monad. So I have a type here. The thing is, this is one of the things that is confusing, is the type constructor thing. So like when you're declaring the data from the other project that I was studying, I know that like the first term is going to be a type constructor. So you would be like having a class on C++ where when you want to instantiate an instance of the class, you're going to use the class name to specify that the variable is going to be of that instance. So that would be like the same as the type constructor on Haskell. The first keyword is the one that you're going to use to instantiate that type. But it's different from C++, obviously, because the type doesn't encode a behavior. It's just like the type. I think that's the main difference, is that on Haskell, you're just going to have the type based on the data. And then later, what's usually going to happen is that you're going to implement the behavior using class types. So you use the class type, and then you declare the type outside, and then you actually implement the behavior of that type on the instance of the class. On C++, it's like you're merging the two, so it's like more constrained. I think that's the main difference. But here, the problem is that I don't know how to read this very well, so I don't know if because also in Haskell, when you have a function, if you don't specify anything, then it's just going to be arguments of the function. So I'm not sure if I'm supposed to read this as M is the type constructor of A, or if this is M is the first argument and A is the second argument of the function. But I'm pretty sure that this is going to be three different functions. The one in the middle is another function, so this would be like a callback function on C++. But it is very confusing. So like this would be like I think the declaration, and then the definition would be you'd pass the actual things. So I think the definition is on the instance. So what comes after the equal sign would be the return statement, and what comes before is the definition of the arguments. But it's very confusing. Maybe functors is easier to see this. So I think a functor is just a map, basically. Or maybe not, it's a map. Let's see the definition of map here. I have to clarify how to read this in a way that makes sense. Coming from another programming language, it's very hard to read this. So I think here what this is doing. So like this would be the definition, the generic definition of the functor. So like is like the template of what the function, what the function should look like for each implementation. And then this would be the implementation for the maybe type of that function template. So the first argument would be this function here. Or maybe this is the name of the function. Yeah, I think this is the name, so it's specifying that it's going to implement this thing here. Then this underscore here would be the first argument. So underscore is the same as Python, but I think is on Python is not explicit. You're not forced to implement this pattern. It's more like a unspoken agreement, let's say. But I think on Haskell you might be forced to implement. Not forced, but yeah, the compiler. I think the compiler understands. But basically, the underscore is like a private variable in Python, and I think Haskell is going to be basically very similar. So it's whenever you don't feel like you need to specify a variable or something, it's like a default thing. So this underscore here would be equivalent to the first segment here. Yeah, but this is the part that I don't know. So I think that's the part I'm struggling to understand. Because here, like in my mind, it doesn't make a lot of sense because the way that I see this is you have a function here. The function returns this one, but this one would be another function that returns this thing. So in my mind, you should have only one. But maybe it's because it's an underscore. Like you should only have the function first. Either you should only have the function or you should have three arguments on the left of the equal sign here. Because whatever is on the right is the return type. So here is just nothing, which is representing FB. And here is just recursing, I think. But I'm not 100% sure about this either. But I think it is. Because usually when they define two different implementations, one's going to be the base case and the other one's going to be the recursion. Yeah, I'm not really sure that's how it works. This one I'm pretty sure that it is a recursion, obviously, because it's just a tree. Yeah, but here it is calling, so maybe the other one is not a recursion, but this one is, because this is going to call fmap recursively to reaches the base case. And then it's passing the same app here, and it's passing left or right to create the nodes from the branch, which is the middle. The branch would be the current node, and the L and R would be left and right. I think it's just some warning, but it's probably just a warning, so maybe it worked. So let me run the other command to see if it worked. So I think it's gonna be this one. And these are the lectures, I think. Yeah, so trines. It is kind of frustrating and very annoying, but I think it's a very good thing that I'm actually very glad that I started learning this because it's a different paradigm, so it forces you to think in a different way. I think it makes it it's gonna make me a better C++ programmer, I think. Another thing that I realized after talking to ChatGPT is that the way the mental model that I had is kind of wrong. like it's on the right direction, but kind of wrong. Because the way that I was thinking before is that you're gonna have functional programming and object-oriented programming on different sides of the spectrum, and then procedural programming is gonna be on the middle of them. But according to, and also I was thinking about functional programming, the wrong side of the polarity. But after talking to ChatGPT, I think it makes a lot of sense. What is said is that functional programming, object-oriented programming is actually on the middle of procedural functional programming. And functional programming is more rigid. I was thinking about functional programming as more solid, as more flexible, let's say, and higher variance. But it's actually the opposite. And the reason why is because functional programming forces immutable states and also doesn't have side effects. And the main driving force, let's say, of flexibility or higher variance and lower density is going to be the mutability of variables and the side effects. So because procedural programming has both of those things, is more on the side of the polarity that it has higher variance and lower density, and functional programming is more on the density and objective side, let's say, because it has immutable states and doesn't have side effects. So then object-oriented programming is going to be somewhere along the middle. But according to ChatGPT, and it's also not exactly on the middle. I think object-oriented programming is closer to functional programming than it is to procedural in the range. And so procedural would be more on the surface of the sphere, let's say. But according to ChatGPT, and I agree as well, is for most cases, procedural programming is going to be the best paradigm. Because I think it's related to the structure of space-time. So most situations, you're going to have higher variance and have more flexibility. So in most cases, I think you do want side effects and you do want mutable states because that's how reality works. But I think as always, I think the larger the project is, the more likely it is that you're gonna have different paradigms. Like the optimal solution would be implementation of different paradigms depending on which side of the project you're on. So like for example, on a web page or something like that, it's very likely that for the front end, it's better to have procedural programming, and for the back end, it's better to have functional programming. But obviously it can change. So basically, like the less the thing that you're doing is going to change, the more inclined you should be to use functional programming. And another thing that is counterintuitive is that ChatGPT says that for scientific simulations and stuff like that, functional programming is better, exactly because of that, because the variables don't change, which is I think I kind of disagree with ChatGPT on that, but I understand the place it's coming from. Because if you are reducing the simulation to a deterministic state, then it makes sense that functional programming is going to be the best, because you already know all the possible states and like you're constraining the simulation. But if you have a simulation that is more close to space-time, I think it's going to shift more towards procedural programming. I think that's one of the reasons why it's very hard to learn Haskell coming from C++, because on Godot I'm used to doing with object-oriented programming, but also even on the object-oriented programming, you have more procedural mindset as well, because the functions inside of the objects do have side effects, and you do have mutability of variables as well. So I think I'm mostly used to having procedural or object-oriented code and not functional programming. So I do think that it's very good to learn Haskell because of that. It forces you to think in a different way. Exercises. To complete the exercise, you need to complete implementation and then missing top level type signatures. You can implement any additional helper functions, but you can't change the names of the given functions. Comments before each function contain explanations and examples of arguments and expected return values. It's absolutely okay if you feel that your implementation aren't perfect. So those exercises after future lectures and improve your solutions if you see any possible improvements. Implement a function that takes true numbers and finds some of their squares. So, let me remember, I think the syntax is gonna be, it's probably, hmm, it already has here. Oh, so this is the decoration I have to implement. So I have to remember which one is which. I think that's the first thing you do is do this thing here. I think you can do num times num or returns num. Num would be one of the built-in types on Haskell, and this goes into the algebraic data type thing, where num contains the integer and floats, I think. I'm not pretty sure if it contains another one, but integer and floats I'm pretty sure. So when you pass an integer, it's going to see that it is inside of the num type, and then it's going to use whatever functionality it has for integer to be able to figure out. Not a function that takes two numbers and finds the sum of their squares. And this is actually default. So it's gonna be actually, yeah, I was confusing with square roots. It's just gonna be. I don't know if you can do this though. I think that's the solution probably. So one thing that I can do is just ask ChatGPT. I don't remember. The thing is how to search for the syntax there. See what syntax is the correct one to use. Trying to see if that I can find the message there. Sum of squares. So the first one's gonna be under 5. I'm gonna try this one. To see if I can pass only the function name there. Sum of hmm. And ask ChatGPT. And ask what is wrong with this. I think what I'm gonna do is just ask questions about the code that I write and not about the exercise. Hmm. And this goes back to the thing I was saying. So I think that here, the way these things work is after you have the arrow here, is going to define a function. So that this would be like a function that returns another function. And this is the thing that I'm struggling to understand how it works. So there's also the, you can have this thing here. I think it's because num is a type constructor. So I'm gonna ask a. The thing is, I wanted to like do a. I didn't want to start with the generic types because I want to understand how to use the built-in ones. But I think yeah. So when you use the this other arrow here, you're basically constraining the generic type. So that's you're basically saying only allow types that are num. I think so. It constrains the generic type to num. Can be any type that belongs to num type class. So I'm gonna see if I can remember this other. It's basically num a with the arrow, and I have a. I'm gonna ask this one first. Because the way that I'm reading this is that takes through numbers as takes through a types as arguments and returns another a type. And the implementation would be x and y, and then you return the what it asks for there. And the way that ChatGPT was saying to do is takes one number as an argument, returns a function. That function takes one number or one type as an argument, a type, and returns another a. So this one I'm struggling to understand. How does that make sense? How does this make sense when you implement the function later? Doesn't make a lot of sense to me. I'm gonna ask after how does this work and why the implementation is the same. So I'll be right back. What ChatGPT is basically saying is that the it is what I not what I was thinking, but according to ChatGPT, which I'm not 100% sure if it's correct or not, but in this case here, A is going to be considered as a type constructor. So the first one that shows up is a type constructor, which means that it doesn't make sense because A is not a type. A is not a type constructor, just a type. So that's the reason why I have to define the other way, because this way is just a function that accepts a type of A and then returns another. So I'm gonna ask why, because like if this is a function that returns another function, how is it possible for you to define the function with this? Or wouldn't in this case the X be a type constructor as well, and then the I? So I'm gonna ask this. Yeah, so in this case, x and y are type constructors. And this is saying that it takes two arguments even though it's written like this. So the thing that makes this hard to understand is because of the black box of the compiler. So like in order to fully understand this, you have to understand what is going on in the compiler that is going to make is going to interpret this as being two arguments and not a function. I think like if, for example, if you put parentheses here, then I'm pretty sure that's going to be interpreting as a function. So it would be a function that receives another function as an argument and returns type A. But if you don't put the parentheses, then it just interprets this as two arguments. So I think maybe I was thinking about it in the wrong way in the beginning. But here, this is like this is the thing that I'm talking about. That's the reason why it's confusing, because here is saying that x and y on the definition are going to be considered as two different arguments. So how is it possible on the declaration that is considered as the first one is considered as a type constructor, but on the definition they are considered as an arguments without the arrow? Those parts is very confusing to understand. I think I'm just gonna ask this as well. I think you have to put it like this. So the answer is not very good, but I was expecting that because it's going to be very hard to. It's basically saying that it's just because of the context, I think it's kind of obvious. but I wanted to understand what is going on under the hood. So why does the context make it different? So I'm gonna ask again. I think I remember seeing this actually, that whenever you have multiple arrows on the declaration, only the last one is going to be the return, and all the other ones are considered as arguments. But I also think I remember, from what I remember on another video somewhere, that they say that it is as if all the functions on Haskell have only one input and one output. So when you're stacking multiple arrows together on the declaration, what is actually happening under the hood is that you're going to have several different functions that get executed sequentially, and then each one is going to be like translating one type to the other. But I'm not 100% sure if that's the case or not. But I am sure that they work as arguments. I'm not sure if they work in this way where there are multiple different functions. They receive one input to have one output. So I'm gonna see if this works here. So now it's a type A constrained by a num, and then returns. So I think it passes, but there are warnings. But the warnings are on other parts of the code, so it doesn't matter. Nice. So it worked. Okay, next one. Implement a function that returns the last digit of a given number. Add function. Don't forget to specify the type in here. I also have no idea how to do this. Hmm. I know that I'm not 100% sure, but I think that the show translates. I remember seeing something like that. But yeah, it's from the videos on the playlist here. He puts he shows an example where he uses show, and then he says you need to, in some situation you need to use not to allow the compiler to understand how you should resolve the string. But I'm not sure if I'm supposed to use this. He's saying that I'm supposed to use mod. So maybe just more simple than this. I think mod by 10 maybe. Yeah, mod by 10. So probably the declaration is gonna be just an int that returns an int. I don't want to use the generic ones. I want to see if I can do it with this built-in types. And then here's gonna be just mod probably, and mod 10. So mod is the remainder. So divides the number by 10 and then returns the remainder. I'm gonna ask how to use mods to ChatGPT. Also, is the other way around. So it's mod first. I think this is probably the answer. I do remember. So I have to. I'm gonna ask. The thing is, I don't remember which video it is, but there is a video where it talks about the. Oh, I passed the wrong function there. There is a video where he talks about how to use the show. I think it is. No, it's not show. I think it's read. So read is another function that reads the string you pass. But there was some. So the example he shows is with a string that says false. And if you specify something to the or you declare something to the compiler, then you're able to use the read function because the compiler is gonna know that it's supposed to translate the string into the Boolean type, and then it works. But if you don't do that, then there's a warning. So I'm gonna ask ChatGPT about this. Hmm. So if fail the negative value. So obviously the easiest thing to try is to change the types. But I wanna understand why it fails with the negative. Uh, Just because I'm curious, I'm gonna do this. Just so this one doesn't work. Let's try this. So I'm gonna try with both sides to see what happens. So both int here, not on the other one, and then the other way around. Hmm. So if I do this. I think it's like this. So it can't be integral. As the question is how to prevent. I wonder if there is a way, for example, to specify to constrain the type to num, but also remove some types that num supports. Because it seems to be complaining that it can't. Num is like inside it, let's say, from the integral is inside of the num type, but then it breaks this because of that. Or maybe it's the other way around. Like the mod is an integral type, and let's see. So now it works. So it was the other way around, but it doesn't work with the value there. Last digit of a negative. Expected true, but 8. Or minus 12. So why is this giving 8? Doesn't make sense. That's ChatGPT. Oh, so yeah, this is the thing you have to do. You have to specify that is bool using the two semicolons here. It's kind of breaking my hand. Why is the remainder? The remainder is gonna be minus 2. There's gonna be one. So it would be minus 2. Would be 10 minus 2, which is 8. But I don't understand why. As obviously if you divide, it's gonna be 1 times 10. The remainder is gonna be minus 2. But it's saying choose mods, so I assume that there is something else. Let's try this, see what happens. Maybe it don't work. Hmm. I'm just gonna watch videos, I think, about this. I'm gonna see if there are videos. So there's a playlist here. This guy has a bunch of papers. This Graham Houghton about Haskell, but I assume it's more advanced stuff. But I wanna watch his videos because obviously I'm not really sure if I can trust this thing here. And it's gonna be annoying either way to solve this, even after. I was thinking about different ways. So, like, I think the easiest way would be to implement another. So, like, if there is a way to differentiate between sign and unsigned, which I think there is probably, you use two different declarations, and then on the negative one, you use one that's gonna work there. You just ask ChatGPT. The positive one, I use the same one that I was using, and that might work. Because then you would call different functions depending on which value it is. But obviously, assume that based on I think that from the perspective of the guy that created the exercises, that's exactly why he created, is because there's this weird thing with mod that for negative numbers is different. So you're supposed to, I saying it's not saying you're supposed to use it, but it's saying as a hint. So I assume that you should use some variation of this. So I'm gonna test to see what happens. I'm gonna test different types here. Ints are already tested, but I'm gonna test floats to see what happens. It doesn't work. So let's see. That mod doesn't work. I don't remember. I'm pretty sure that they don't have unsigned integer as a built-in type. I think it's only int here somewhere. Basic types. So it's bool, int, integer. Let's try this one. I don't think it's gonna work, but I just wanna see. I was gonna test to see if it works. Yeah, it fails on the same one probably. Yeah. Yeah, so I think it fails. This is probably the easiest way to fix this. So it'll be if n is greater than 0, you do mod thing, else you just translate the number into a positive. Let's see if this works. What should be the other way around? But I'm not really sure if it's gonna work either way. Nice, worked. So I'm not really sure if this is a solution that the guy wanted. I think that there are obviously several other solutions. So another one would be to implement there, implement another function here. But I think that this other one wouldn't work because of there isn't a type. But obviously you can create another type. But I don't think it's worth it to do this. Maybe it is, not sure. So I think like you could create another type that would work as an unsigned integer. Which would just be extra steps to do the same thing I think here. But just to practice, I could do that. So I could create a type that I don't know how it works very well here. I think from what I've seen, you should use the same. Then you could create a class that implements this type. I think you have to use like this. I don't remember. And then on this one, you implement last digits. Then you do unsigned int. And then you define. Yeah, but I think it's not worth it. So obviously I would have to iterate a couple of times to see if this was gonna work. But I would basically just do the same thing that I'm doing here on the function here. So just test to see if the number is greater than 0. Then return the number. And then I could use this other type that I created, which is unsigned int. In this case would be the constructor and then receives an int. But I think, yeah, so here probably it would be like this. So it takes a constructor and returns int. So the way that you would use it is by passing this. So on this function here, I would change accept this type. And then I would remove this and I would just do the mod n10 here. So this one, the type here would check to see if n is greater than 0. You would return like the opposite if it's lower. If it's a negative number, it just converts to positive. Got it? It's whatever. So I'm just gonna spend 15 minutes reading the book there. Then I'm gonna stop streaming. I'm probably just gonna watch videos off stream and then I'll continue this some other time. This exercise. Maybe I'll do the other exercises off stream. It's probably a good idea to do them. I think probably gonna watch the lectures again from the guy. Then I'm going to try some of the exercises. I think it's good to do the exercises because it forces you to think about the stuff that you don't understand very well. But like the thing that I don't like about exercises is like the kind of the elite code mentality, let's say. I don't like I don't if these exercises are too much like thinking about stuff that is not related to the language itself. So for example, having to figure out this thing here, or I want to do mainly things that force me to understand or to think about the language, and not spend time like trying to figure out stuff that doesn't matter to me. So if the exercises are not mainly to understand the, but I guess what I can do is just ask the solution for ChatGPT and then see if it works. Because the main thing is to learn or to think about what parts of the language I'm struggling to understand the concepts from from first principles, fundamental first principles, and I want to finish this fast so I can study the repositories. I think I'm not going to study the other one that I was studying before because it's not the main thing that I search for the other topics on Perplexity and ChatGPT, but I think that these other repositories don't use Haskell. So I'm not gonna need to learn Haskell. But the main priority is to, I think I'm gonna focus on this one because it's a more complete repository. And then, because the other one I would have to study the libraries that they use anyway, so I think that it might be a waste of time. It might be better to just focus on this one, which is like a bigger project and probably implements more stuff that is related to types than the other one. So I think I'm gonna spend some time on this. So do after learn a decent amount of the Haskell to understand how it works. I'm just gonna spend so much time studying this repository here. And I want to be careful to not spend too much time. Oh, they have a reference to the other one here. So I can look into these other repositories as well. And these ones might be interesting as well. But my main focus is on the type theory and not. So I want to understand more to bridge the gap between the category theory stuff on theoretical side and how the implementation of those concepts work on an actual programming language. That's why I'm studying Haskell now. But the main thing is Godot. I don't want to be too sidetracked by this, so I have to go back to Godot soon and also finish the assembly exercises. So I don't want to spend too much time on this. Once I feel like I understand the main concepts very well, I'm just gonna focus more on the. I just need to learn enough so I'm able to read the repositories without struggling to understand how it works. And I think I'm getting to the point because the most difficult part is this stuff about the types. But also, yeah, probably the best thing to do is just gonna be to study the thing right away. So I think I'm not gonna spend too much time on these exercises. I'm just gonna look at the solution of each one. And then I'm gonna focus most of the time reading the repository and trying to understand already because I don't have too much time to study this stuff. Then maybe later at some other points I'll come back to this. So I'm going to read the book there now. I'm gonna have to watch the videos as well. I'm gonna spend 15 minutes reading this with the text-to-speech.
You can query types for functions, partially applied functions, and values, which are, in a way, fully applied functions. When we query the types of values, we see something like this. Prelude greater than type char. Prelude greater than type Julie char.
Be right back.
Prelude greater than type true. True bool, that's the type char. Julie has the type string. True has the type bool. When we query the types of numeric values, we see type class information instead of a concrete type, because the compiler doesn't know which specific numeric type a value is until the type is either declared, or the compiler is forced to infer a specific type based on the function. For example, 13 may look like an integer to us, but that would only allow us to use it in computations that take integers and not, say, in fractional division. For that reason, the compiler gives it the type with the broadest applicability, most polymorphic, and says it's a constrained polymorphic none greater than a value. Prelude greater than type 13. 13 none a equal to greater than a. Chapter 5. Types 121. We can give it a concrete type by declaring it prelude greater than let x equal to 13. Integer prelude greater than txx. Integer. Polymorphism, polymorphic numerals, and type inference will all be addressed in more detail later. You can also query the type signatures of functions as we've seen. Prelude greater than type not bool greater than bool. This takes one input of a bool value and returns one bool value. Given that type, there aren't too many things it even could do. Understanding the function type, the arrow greater than is the type constructor for functions in Haskell. It's baked into the language, but syntactically it works in very much the same way as all the other types you've seen so far. It's a type constructor like bool, except the greater than type constructor takes arguments and has no data constructors. Prelude greater than info, greater than data, greater than a b. Some further information is allotted. If you compare this to the type constructor for the two tuple u, see the similarity. Prelude greater than info, data, a b. We saw earlier that the tuple constructor needs to be applied to two values in order to construct a tuple. A function must similarly, 4 to be precise. But if we assume that the standard prelude functions are generally useful functions, it helps narrow it down considerably. Later we will show you how to calculate the cardinality of types, such that you will know how many ways there are to define something of a particular type. Have two arguments, one input and one result in order to be a function. Unlike the tuple constructor though, the function type has no data constructors. The value that shows up at term level is the function. Functions are values. As we've said, the hallmark of a function is that it can be applied, and the structure of the type demonstrates this. The arrow is an infix operator that has two parameters and associates to the right, although function application is left associative. The parameterization suggests that we will apply the function to some argument that will be bound to the first parameter, with the second parameter, b, representing the return or result type. We will cover these things in more detail throughout this chapter. Let's return to reading type signatures. The function fst is a value of type a, b, greater than a, where greater than is an infix type constructor that takes two arguments, fst a, b, 1, a, 2, 3, 1. The first parameter of fst has the type a, b. Note that the tuple type itself takes two arguments a and here. 2. The function type greater than has two parameters here. One is a, b, and one is the result of. 3. The result of the function, which has type a. It's the same a that was in the tuple a, b. How do we know it's the same a? As we learn more about type variables, it will become more clear how we know. We can say that we know the input type a and the output type a must be the same type, and we can see that nothing happens between the input and the output. That is, there's no operation that comes between them that could transform that a into some other value of that type. We'll go into more detail about those points later in the chapter. Let's look at another function. Prelude greater than type length. Length a greater than int. Chapter 5. Types 123. The length function takes one argument that is a list. Note the square brackets and returns an int result. The int result in this case will be the number of items in the list. The type of the inhabitants of the list is left unspecified. This function does not care. In fact, cannot care what types of values are inside the list. Type class constrained type variables. Next, let's look at the types of some arithmetic functions. You may recall that the act of wrapping an infix operator in parentheses allows us to use the function just like a normal prefix function, including being able to query the type. Prelude greater than type. Num a equal to greater than a, greater than a, greater than a. Prelude greater than type. Fractional a equal to greater than a, greater than a, greater than a. To describe these casually, we could say addition takes one numeric argument, adds it to a second numeric argument of the same type, and returns a numeric value of the same type as a result. Similarly, the fractional division function takes a fractional value, divides it by a second fractional value, and returns a third fractional value as a result. This isn't precise, but it will do for now. The compiler gives the least specific and most general type it can. Instead of limiting this function to a concrete type, we get a type class constrained polymorphic type variable. We'll save a fuller fuller explanation of type classes for the next chapter. What we need to know here is that each type class offers a standard set of functions that can be used across several concrete types. When a type class is constraining a type variable in this way, the variable could represent any of the concrete types that have instances of that type class, so that specific operations on which the function depends are defined. For that type, we say it's constrained because we still don't know the concrete type of A, but we do know it can only be one of the types that has the required type class instance. This generalization of number could is what lets us use the same numerical literals to represent numeric values of different types. We can start with a num A equal to greater than a value and then create specific versions of it with a concrete type using a to assign a type to the value. Chapter 5, types 124,124. Preludes let 15 15 prelude greater than T15 15 none A equal to greater than a prelude greater than let 15 and equal to 15. In prelude greater than let 15 double equal to 15. Double prelude greater than T15 and 15 int. In prelude greater than T15 double 15 double double. We went from num A equal to greater than A to int and double. This works because int and double each have an instance of the none type class. Prelude greater than info none. Irrelevant bits elided. Instance none intent defined in GHC num instance none double defined in GHC float. Since they both have instances of none, the operations from num such as addition are defined for both of them. Prelude greater than 15 and 15 int. 30 prelude greater than 15 double 15 double. 30. We can also make more specific versions of our none and greater than a value named 15 by using it in a way that requires it to become something more specific. Prelude greater than 15 double 15. 30. Prelude greater than 15 int 15. 30. What we cannot do is this. Prelude greater than 15 double 15 int could match expected type double with actual type int. Chapter 5, types 125. In the second argument of namely 15 int, in the expression 15 double 15 int, we can't add those two values because their types are no longer polymorphic and their concrete types are different, so they have different definitions of how to implement addition. The type error message contrasts the actual type with the expected type. The actual type is what we provided. The expected type is what the compiler expected. Since we had 15 double as our first argument, it expected the second value to also have the type double, but it actually has the type int. A type signature might have multiple type class constraints on one or more of the variables. You will sometimes see or write type signatures such as num A num B equal to greater than A greater than B greater than B or A num A equal to greater than a greater than a greater than ordering. Here the constraints look like a tuple, but they don't add another function argument that you must provide, and they don't appear as a tuple at the value or term level. Nothing to the left of the type class arrow equal to greater than shows up at term level. The tuple of constraints does represent a product or conjunction of constraints. In the first example above, there are two constraints, one for each variable. Both A and B must have instances of the num type class. In the second example, both of the constraints are on the one variable A, that is, must be a type that implements both ord and num. Exercises. Type matching. Below you'll find a list of several standard functions we've talked about previously. Under that is a list of their type signatures. Match the function to its type signature. Try to do it without peeking at the type signatures either in the text or in GHCI, and then check your work. You may find it easier to start from the types and work out what you think a function of that type would do. Chapter 5, types 126. 1. Functions. A not. B length. C concat. D head. ELT2. Type signatures. A greater than A. A greater than A. Type C. D a greater than in. E or equal to greater than a greater than a greater than bool. Currying. As in the lambda calculus, arguments plural is a shorthand for the truth in Haskell. All functions in Haskell take one argument and return one result. Other programming languages, if you have any experience with them, typically allow you to define functions that can take multiple arguments. There is no support for this built into Haskell. Instead, there are syntactic conveniences that construct curry functions by default. Currying refers to the nesting of multiple functions, each accepting one argument and returning one result, to allow the illusion of multiple parameter functions. The arrows we've seen in type signatures denote the function type. We looked at the data type definition earlier, but let's review. Data greater than B. In order to have a function, you must have one input, the A, to apply the function to, and you'll get one result, the B, back. Each arrow in a type signature represents one argument and one result, with the final type being the final result. If you're constructing a function that requires multiple parameters, then the B can be another function. The A can be another function as well, which we'll look at. Chapter 5, types 127. More later. In that case, just like in lambda abstractions that have multiple heads, they are nested. Let's break this down by looking at the type signature for addition. A function that needs multiple inputs. Num A equal to greater than a greater than a greater than A. 1. Num A equal to greater than a greater than a greater than A. 2. Num A equal to greater than a greater than a greater than a greater than 1. Here's the type class constraint saying that it must have an in. Stance of num. Addition is defined in the num type class. 2. The boundaries of 2 demarcate what you might call the two parameters to the function, but all functions in Haskell take one argument and return one result. This is because functions in Haskell are nested like Matryoshka dolls in order to accept multiple arguments. The way the greater than type constructor for functions works means a greater than represents successive function applications, each taking one argument and returning one result. The difference is that the function at the outermost layer is actually returning another function that accepts the next argument. This is called currying. 3. This is the result type for this function. It will be a number of the same type as the two inputs. The way the type constructor for functions GT is defined makes currying the default in Haskell. This is because it is an infix operator and right associative. Because it associates to the right, types are implicitly parenthesized like so. F A greater than a greater than A associates to F A greater than a greater than A. Chapter 5, types 128 and map A greater than B greater than A greater than B associates into map a greater than B greater than A greater than B. Let's see if we can unpack the notion of a right associating infix operator giving us curry functions. The association here, or grouping into parentheses, is not to control precedence or order of evaluation. It only serves to group the parameters into argument and result, since there can only be one argument and one result per arrow. Since all the arrows have the same precedence, the associativity does not change the precedence or order of evaluation. Remember, when we have a lambda expression that appears to have two parameters, they're actually nested lambdas. Applying the expression to one argument returns a function that awaits application to a second argument. After you apply it to a second argument, you have a final result. You can nest more lambdas than two, of course, but the process is the same. One argument, one result, even though that result may be a function awaiting application to another argument. The type constructor for functions and the types we see above are the same thing but written in Haskell. When there are two arguments in Haskell, we apply our function to an argument, just like when we apply a lambda expression to an argument, and then return a result that is a function and needs to be applied to a second argument. Explicit parenthesization, as when an input parameter is itself a function such as in map above, may be used to indicate order of evaluation, but the implicit associativity of the function type does not mean the inner or final set of parentheses, i.e. the result type, evaluates first. Application is evaluation. In other words, the only way to evaluate anything is by applying functions, and function application is left associative. So the leftmost or outermost arguments will be evaluated first, assuming anything gets evaluated. Since Haskell is non-strict, you can't assume that anything will be evaluated, but this will be more clear later. Partial application. Currying may be interesting, but many people wonder what the practical effect or value of currying is. We'll look now at a strategy called partial application to see what currying does for us. It's something we'll explore more as we go through the book, but we'll start with a relatively uncomplicated example. We use the double colon to assign a type. Making the type concrete will eliminate the type class constraint. Add stuff integer greater than integer greater than integer. Add stuff of b equal to a b5. So add stuff appears to take two integer arguments and return an integer result. But after loading that in GHCI, we see that it is taking one argument and returning a function that takes one argument and returns one result. Prelude greater than t add stuff. Add stuff integer greater than integer greater than integer. Prelude greater than let add 10 equal to add stuff 5. Prelude greater than t add 10 integer greater than integer. Prelude greater than let 15% equal to add 5. Prelude greater than 15. 15 prelude greater than add 15. 25 prelude greater than add stuff 5 seconds. 15. Here 15 is equal to add stuff 5 5 because add 10 is equal to add stuff 5. The ability to apply only some of a function's arguments is called partial application. This lets us reuse add stuff and create a new function from it with one of the arguments applied. If we recall that is a type constructor and associates to the right, this becomes more clear. Add stuff integer greater than integer greater than integer, but with explicit parenthesization. Add stuff integer greater than integer greater than integer. Applying add stuff to one integer argument gave us the function add 10, which is the return function of add stuff. Applying add 10 to an integer argument gives us a return value. So the type of 15 is integer, no more function arrows. Let's check our understanding with a function that isn't commutative. Subtract stuff integer greater than integer subtract stuff xy equal to xy 10. Subtract tone equal to subtract stuff 1. Prelude greater than t subtract tone integer greater than integer. Prelude greater than let result equal to subtract tone 11. Prelude greater than result minus 20. Why do we get this result? Because of the order in which we applied arguments. Result is equal to 1 to 11 minus 10. Manual currying and uncurrying. Haskell is curried by default, but you can uncurry functions. Uncurrying means nesting the functions and replacing the two functions with a tuple of two values. These would be the two values you want to use.
So I think he's talking about exactly the question that I had before. And it seems to be the way that I was thinking that it works. So each arrow has only one argument and returns, so it has one input and returns one output per arrow. So this would be like a function that receives an integer as an argument and returns another function. But it's still, so he's saying basically that the reason why this works is because of this concept of partial application, but I still don't understand how the compiler thinks about this. Now, the definition is the thing that is very confusing to me, because if you're gonna call the function with one argument here, how does it work? How does it get you the final result? It wouldn't make sense that the first time you call this, it's going to return another function. So it's basically just replacing one of the arguments, which would be the x, and then returning another function that depends only on y. But I don't understand how is possible to return everything. I don't think he explained so far how this works. So here it has a result, and then it's already like the final thing. So we're passing 11 here. But how? Oh no, this is a different thing. So here is so here is using twice. So like this would be exactly that what I was saying before. So it would be. But the thing that is weird is that if this was 1, if the x was 1 here, it would be minus y minus 9. Oh, so yeah, that makes sense. So it's minus 20 because it's the result. So this one would be the partial application of this. So when you call the first time here, it only replaces x by 1, which gives you another function that has y equals minus y minus 9. Because it's 1 minus 9 is 9. Then when you call the function again with 11, you get the result. But the thing that is very confusing to me is the relationship between the definition and the declaration. Because on other programming languages, obviously, you like it's not decoupled like that. The declaration, the definition. You would have both in the declaration, you would have a function that returns another function, and on the definition, you would have the return statement with the other function. And then you wouldn't be able to call that function directly with the true values. So this is the thing that I don't understand. I don't think he's gonna talk about it as well. Obviously, he's saying it's because of currying. So currying is the principle of returning another function from some function. It's basically what currying is, which allows you to like cache a result, let's say. Because the first time you call the function, you're just getting another function. So, but it doesn't explain this relationship between how you use the arguments here on the definition and how the arguments work on the declaration, and then how that relates to the way you call the function as well. So it's very confusing. This is one of the things that I don't dislike the most about Haskell so far. It's both this stuff and on the type declarations, the way that is written, a lot of the time is very confusing to understand how it works.
Arguments. If you uncurry, the type changes from none equal to greater than a, greater than a, greater than a to num, a equal to greater than a greater than a, which better fits the description, takes 2 arguments, returns 1 result in curried functions. Some older functional languages default to using a product type like tuples to express multiple arguments. Uncurried functions, 1 function, many arguments. Curried functions, many functions, 1 argument apiece. Chapter 5, types 131. You can also sugar the automatic currying yourself by nesting the arguments with lambdas, though there's almost never a reason to do so. We'll use anonymous lambda syntax here to show you some examples of uncurrying. You may want to review anonymous lambda syntax or try comparing these functions directly and thinking of the backslash as a lambda, nonsense, bool, greater than integer, nonsense, true, equal to 805, nonsense, false, equal to 31,337. Curried function, integer, greater than bool, greater than integer. Curried function ib equal to 1 nonsense b. Uncurried function, integer, bool, greater than integer. Uncurried function ib equal to 1 nonsense b. Anonymous integer bool, greater than integer, anonymous b, nonsense b. And a nested integer, greater than bool, greater than integer. And a nested equal to 11 to 16 minus 1 nonsense b. Then when we test the functions from the REPL, prelude greater than curried function 18 false 31,347. Preludes anonymous 10% false 347. Prelude greater than nested 1047. 347. Prelude greater than nested 10%. In nested we manually nested the anonymous lambdas to get a function that was semantically identical to curried function but didn't leverage the automatic currying. This means functions that seem to accept multiple arguments such as with a greater than a greater than a greater than are higher order functions. They yield more function values as each argument is applied until there are no more greater than type constructors, and it terminates in a non-function value. Currying and uncurrying existing functions. It turns out we can curry and uncurry functions with multiple parameters generically without writing new code for each one. Consider the following example for currying. Preludes let curry fab equal to fab. Prelude greater than t curry. Curry t1 t2 t1 greater than t2 greater than t. Prelude greater than tfs. FST AB greater than a prelude greater than T curry FST curry FST TBT prelude greater than FST 1 2 1 prelude greater than curry FST 12 1. Then for uncurrying prelude greater than let uncurry FAB fab prelude greater than T uncurry uncurry T1 greater than T2 T T1 T2 greater than T prelude greater than T num A equal to a greater than A prelude greater than 1.2 3 prelude greater than uncurry 1 2 3 currying and uncurrying functions of 3 or more arguments automatically is quite possible but trickier. We'll leave that be but investigate on your own if you like. Sectioning. We mentioned sectioning in chapter 2 and now that we've talked a bit more about currying and partial application it should be more clear what's happening there. The term sectioning specifically refers to partial application of infix operators which has a special syntax and allows you to choose whether the argument you're partially applying the operator to is the first or second argument. Prelude greater than let x equal to 5 prelude greater than let y equal to 24 prelude greater than let z equal to 2 prelude greater than yx 32 prelude greater than zx 25. With commutative functions such as addition the argument order does not matter. We will usually section addition as for example 3 but later when we start using partially applied functions a lot with maps and folds and so forth you'll be able to see the difference that the argument order can make with non-commutative operators. This does not only work with arithmetic though. Prelude greater than let celebrate equal to woot prelude celebrate nap time nap teen woot prelude celebrate dogs woot. You can also use the syntax with functions that are normally prefix if you use the backticks to make them infix. Note the is a shorthand for constructing a list of all the elements between the first and last values given. Go ahead and play with this in your rebel. Prelude greater than elan 9 110 true prelude 9 elan 110 true prelude greater than let's elan 110 prelude greater than 9 euros true prelude greater than c25 false. If you partially applied elan in its usual prefix form then the argument you apply it to would necessarily be the first argument. Prelude greater than let hasten equal to lm 10 prelude greater than hasten 1 9 false prelude greater than hasten 5 15 true. Partial application is common enough in Haskell that over time you'll develop an intuition for it. The sectioning syntax exists to allow some freedom in which argument of a binary operator you apply the function to. Exercises. Type arguments given a function and its type. Tell us what type results from applying some or all of the arguments. You can check your work in the rebel like this using the first question as an example. Prelude greater than let f a greater than a greater than a greater than a f equal to undefined prelude greater than let x char x equal to undefined prelude greater than tfx. It turns out that you can check the types of things that aren't really implemented yet so long as you give GHCI an undefined to bind a signature to. 1. If the type of f is a greater than a greater than a and the type of r is char then the type of fx is chapter 5 types 135 a char greater than char bx greater than x greater than x greater than xca greater than a greater than a da greater than a greater than a greater than char. 2. If the type of G is A greater than B greater than C greater than B then the type of G0C woot is A string B char greater than string C and D char. 3. If the type of H is num A num B equal to greater than A greater than B greater than B then the type of H12 is A and BD num B equal to greater than B. Note that because the type variables A and B are different the compiler must assume that the types could be different. If the type of H is num A num B equal to greater than A greater than B greater than B then the type of H1 5.5 double is A integer B fractional B. 5th. If the type of Jackal is ORed A greater than A then the type of Jackal keyboard has the word Jackal in it. Chapter 5 types 136 DBEEQ equal to greater than B greater than char. 6th. Of Jackal keyboard. 7th. If the type of Kes B greater than A integer B if the type of Kes B greater than 9. Chapter 5 type 137 a num A equal to greater C integer denum A or A equal to greater than A EA 5.5 polymorphism. Polymorph is a word of relatively recent provenance. It was invented in the early 19th century from the Greek words poly for many and morph for form. The IC suffix in polymorphic means made of so polymorphic means made of many forms. In programming this is understood to be in contrast with monomorphic made of one form. Polymorphic type variables give us the ability to implement expressions that can accept arguments and return results of different types without having to write variations on the same expression for each type. It would be inefficient if you were doing arithmetic and had to write the same code over and over for different numeric types. The good news is the numerical functions that come with your GHC installation and the prelude are polymorphic by default. Broadly speaking type signatures may have 3 kinds of types: concrete, constrained polymorphic or parametrically polymorphic. In Haskell polymorphism divides into 2 categories: parametric polymorphism and constrained polymorphism. If you've encountered polymorphism before it was probably a form of constrained often called ad hoc polymorphism. Ad hoc polymorphism 2 in Haskell is implemented with type classes. Parametric polymorphism is broader than ad hoc polymorphism. Parametric polymorphism refers to type variables or parameters that are fully polymorphic. When unconstrained by a type class their final concrete type could be anything. Constrained polymorphism on the other hand puts type class constraints on the variable, decreasing the number of concrete types it could be, but increasing. 2 Wadler's paper on making ad hoc polymorphism less ad hoc. mit.edu/dnj/teaching/6898/papers/wadler88.pdf. Chapter 5 types 138 what you can actually do with it by defining and bringing into scope a set of operations. Recall that when you see a lowercase name in a type signature it is a type variable and polymorphic like at etc. If the type is capitalized it is a specific concrete type such as int, bool, etc. Let's consider a parametrically polymorphic function identity. The id function comes with a Haskell prelude and is called the identity function because it is the identity for any value in our language. In the next example the type variable a is parametrically polymorphic and not constrained by a type class. Passing any value to id will return the same value. id a greater than a for all a get an argument of some type a return value of same type a. This is the maximally polymorphic signature for id. It allows this function to work with any type of data. Prelude greater than id 1 prelude greater than id blah prelude let inc 1 prelude greater than inc 2 3 prelude id inc 2 3 based on the type of id.
Oh, I'm gonna stop here. The timer ran out. So I'm gonna continue reading the book of string. I'm gonna finish watching these videos here. I'm gonna watch these other videos and go back to I'm gonna watch the lectures again. And I think what I'm gonna do is just I'm gonna paste this thing here on GPT and then see the solution. I might try to spend some time trying to solve. Like I said, I don't have a lot of time, so also I'm not really sure if I should. I think I might like leave this for later because I need to finish the assembly stuff still. So I want to finish the assembly exercises first, probably, so I can have the Anki cards and I can start training because I haven't started training on the Anki cards with assembly. I was waiting for learning Haskell so I can spend more time focused on Haskell first. But I think now is probably a good time to finish the assembly exercises. Then I'm just gonna practice on Anki, the assembly, as I learn the other stuff. So like probably like 15 minutes a day or something like that. I just do Anki cards for assembly after I finish the exercises. And as I do that stuff, then I study this thing here, and I should go back to continue the point where I stopped on Godot last time. I think I have to get back to that as fast as possible. So yeah, probably I'm gonna stop this Haskell now, and I'm gonna focus on finishing the assembly thing. And I'm going to continue learning Haskell off-stream probably, but I'm going to focus more. I'm going to go back to Godot's until I finish this thing, the first thing that I have there. Once I finish that thing, then I can go back to this stuff here, because then I'm going to focus more on this side of things instead of this thing might take a lot of time because there's still a lot of stuff that I have to figure out. So that's the reason why I think it's probably going to be better to go back to Godot stuff. So probably next time that I stream, I'm just going to finish the assembly exercises. And then after that, I'm going to continue from where I stop on the Godot stuff. And I'm going to continue to, off stream, I think I'm just going to focus on Haskell still until I finish probably I'm just going to finish the exercises, finish the book, this book here, and watch more content. And then that's probably going to be it. I don't think I'm going to spend a bunch of time like trying to build stuff or anything like that. I just want to understand enough, like have a very good baseline of the concepts that I don't understand, so I can read this repository here, and also in the future if I need to learn other functional programming languages or stuff like that. I think it's a good thing to learn at least one functional programming language, because it definitely is expanding the way that I think, especially when it comes to types. I think for the types stuff is very good to learn this, so I don't regret learning Haskell so far. Yeah, next time I'm probably gonna focus on the assembly exercises, so see you then.